Hello dear students, how are you all doing? I hope you are all taking good care of yourself and staying happy and healthy. Welcome back to the channel Pen and Paper Chemistry, and today I'm going to take up the topic of diazonium salts. It's another interesting cousin of the compound that we did in our earlier video, Grignard's reagent. You shall be doing the chemical properties or preparations using diazonium salts. You may not have it as a separate topic in your syllabus, but you will come across many reactions where you will be dealing with diazonium salt. So for example, Sandmeyer reaction, Gattermann reaction, and so on. So let's understand diazonium salts as one single topic. But before we do that, please make sure that you have your pen and paper ready to take down the notes. Diazonium salts, or more specifically aryl diazonium salts, what are they? Salts. That means there will be a plus and a minus. That means there will be ions in this, as you can see from the structure. But before I go on to that, let me take up the breakup of each. Aryl. You remember from methane, if you remove a hydrogen, you get what we call as a methyl with one free valency, one bond still available, right? Same way, I have benzene. I remove one hydrogen from it and I have one free valency in the resulting alkyl group, what we call as the phenyl group, C6H5. And that gives us the first part of these compounds, aryl. One free valency. Diazonium. Diazonium stands for this group where nitrogen is bonded to another nitrogen, but unlike in nitrogen gas where they are happy in their own world after forming a triple bond, the electrons of nitrogen, they form a bond with the benzene ring here. With the result, it is short of electrons and acquires a positive charge. Now, because it acquires a positive charge, it will need something negative to balance it. And that gives us the resulting salt, what we call as the aryl diazonium salt in general. They have their specific names as well. Now, what is the negative part here? If you notice, I have already written the chloride in the above example. We also can have a bromide, nitrite, bisulfate, tetrafluoroborate, balancing the positive charge on the nitrogen. So how do we name them? Naming them happens on the basis of the parent hydrocarbons. So here I have the name as benzene diazonium chloride. Simple. Benzene diazonium chloride. Try naming this compound. Benzene diazonium nitrite. Well done. So the naming of these compounds is pretty simple. Now, some of you may be having a doubt still as to why we are writing a positive charge on the nitrogen. I'm going to go back to the concept of Lewis structures. If you remember, in one of my previous videos, I have given you a very simple way of drawing the Lewis structures and calculating formal charge. So I'm taking up from there. Formal charge is given by, this Fc stands for formal charge, is given by the number of valence electrons. Take away the number of bonds formed by the atom and the number of electrons of the lone pair. So let us calculate the formal charge on, let's say I'm talking about the first nitrogen, I'm going to underline it in red. So if you see the formal charge on this nitrogen, the number of valence electrons, because the electronic configuration is 2 and 5, so it's 5. Now how many bonds has it formed? 1, 2, 3, and there's a fourth one. So 5 take away 4 gives me a value of +1. What's the formal charge on my nitrogen, which I'm going to underline now in yellow? Yes. So again 5 minus 3 minus the lone pair of electrons. So how many lone pairs will it have? Look at the structure, draw the structure yourself, and then tell me how many lone pairs. Yes, one lone pair. But why have I put a 2 over here? Because here we have to take the number of electrons of the lone pair, not the number of lone pairs. So how many, what value do we get here? Yes, we get a value of 0. So overall our diazonium group has a positive charge. And as we explained earlier, the positive charge is balanced by the negative charge of the anion. Right? Good so far? Let us now discuss why are aryl diazonium salts more important than the alkyl diazonium salts. The answer would be very clear from the structure itself. So for now, I'm going to keep the negative anion, or the anion aside, and look at the structure. Can you recall something over here? You have the aromatic ring and you have the bonded. Yes. So what happens here? The nitrogen tries to take up the electrons. Yes, very good. If you could guess that we are going to talk about a resonance over here. So it is again like the classic game of passing the parcel, or yes, monkey in the middle. That's the analogy that I like to use. So with the result, what will happen is, because of resonance taking place, why don't you pause the video and draw the structures yourself? It will give you confidence in the topic of resonance as well. Look at the charges on the molecules. So here, in the case of nitrogen, the formal charge on nitrogen, see over here, 5 is the number of valence electrons. Take away the 4 bonds it is forming, gives us a charge again of +1. And because electrons have been withdrawn from this carbon, this acquires a positive charge. Now this this carbon tries to satisfy itself, and there we have a positive charge here. Double bond N, double bond N, and this will have now 2 pairs of electrons as lone pairs. What about the third structure? Again, what will happen is it will try to withdraw electrons. With the result, this carbon now becomes electron deficient. So you see, in the case of aryl compounds, there is a resonance stabilization which is possible. Interestingly, your syllabus may not require you to draw the structures or study the aryl diazonium salts in so much detail. So in case that is not required and you don't want to take too much tension, you can ignore these structures for now. But don't ignore resonance. It's the basic backbone of organic chemistry. Let's see if such kind of resonance structures are possible in the case of alkyl diazonium salts. No, we know that very clearly, right? 1, 2, 3, 1, 2, and N triple bond N positive, Cl negative. There is no resonance stabilization in the case of alkyl diazonium salts. That is why the aryl diazonium salts are much more important as compared to the aryl ones. Have you noted this down? Do we go on to the next video? Oh, no, 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 no. I am yet to talk to you about the preparation of diazonium salts. Now, for the preparation, we simply have to treat aniline with nitrous acid, and nitrous acid is HNO2. Now, as you may have already done, nitrous acid you will not find in your laboratory reagents easily. It's a very unstable acid. It tends to get oxidized. So what we do is we prepare nitrous acid in situ. In situ means in the reaction mixture itself. Now when we prepare, we take sodium nitrite and HCl, and a very important condition of this reaction is the ice cold bath conditions. That means you carry it out in a test tube, of course, when you will do it in the laboratory, but that test tube is put in ice cubes. It's a very interesting experiment when you do it in the laboratory. I'm sure you'll get a chance to do that. So when you carry out the preparation, you react aniline with nitrous acid being generated in situ, and we have again benzene diazonium. So in short, we write it as N2 positive Cl negative. Don't forget the positive and the negative. So we have benzene diazonium chloride plus NaCl. What other products will be formed? Well done. And water will be formed. You see, we took one part of the aniline and we got one part of the benzene diazonium salt in stoichiometric proportions, right? Have you noted this down? Please don't forget a very important condition of this preparation. And this reaction where we are forming the diazo bonding is known as diazotization. You must have studied it under benzene and chlorobenzene. Also, we did discuss a part of diazotization steps. Noted? Because now we are going to discuss the properties. It is interesting to note that they are otherwise colorless compounds, but they turn brown when they are exposed to air. They are unstable, very unstable, and a very interesting part is that they are explosive in nature. That is why benzene diazonium chloride or these diazonium salts are never separated from the solution, because they have been found to explode. So what we do is, just like in Grignard's reagent, we prepare them and we use them right away, or we prepare them when they are required to be used. So although you will be doing this experiment in the laboratory as I mentioned, but there will be other compounds that you will be adding to them right away as soon as you prepare. In fact, you will be doing the reactions under ice cold conditions. What about their solubility? You notice I put a question mark over here. Think about it. They are ionic compounds. So what kind of behavior will they show? In what type of compounds will they be soluble? Yes, they will be soluble in water. That means they are soluble in polar solvents, water, alcohol, slightly soluble in acetic acid as well. But if you talk about solubility in ether, no. So you see, they are close to each other, Grignard's reagent and diazonium salts. But Grignard's reagent, remember, we were keeping them in dry ether, completely dry ether. So they are cousins, but opposite cousins, right? They don't really gel. What about their behavior as electrolytes? Yes, again, because they are made up of ions N2 positive, Cl negative, their aqueous solutions can behave as electrolytes. That means they will be able to conduct electricity because of the presence of ions in them. Isn't it interesting? We come across organic compounds which are ionic. In my next video, we are going to discuss about the properties and what all preparations can be done using these diazonium salts. So if you notice, we can prepare a large number of compounds like benzene, phenol, chlorobenzene, bromobenzene. There are different methods by which you can do that. We are also going to prepare nitrobenzene, fluorobenzene, which are otherwise difficult to prepare by substitution alone, because we know that aromatic compounds do not undergo nucleophilic substitution. So by the time I load the next video, please make sure that you have revised whatever we have done in today's lesson, and don't forget to practice the preparation equation, a very, very important equation. See you in the next video. Stay connected and stay healthy.